Hi, I'm Amber, and in this video I'm going to be taking you through the MO energy diagram for NO. NO being nitrogen and oxygen. So to start this off, we're going to have to work out the basis set for both nitrogen and oxygen. The basis set is just the electron configuration of the outermost shells. So for nitrogen, this is 2s2, 2p3, and oxygen is 2s2, 2p4. So after this, we can work out the atomic orbitals for both N and O. So for nitrogen, we have 4 atomic orbitals, and similarly for orbitals. Now from this, we know that we all together have a total of 8 molecular orbitals. In this diagram or question, we haven't been given any orbital energies to compare off. However, of our knowledge of the periodic table, we know that nitrogen and oxygen are right next to each other, so there should be little difference in energies. So, starting with this, we know that nitrogen has 5 electrons and oxygen has 6 electrons. So altogether, NO must have 11 electrons. So to set up our diagram, we start with denoting the 2s orbital down here for both oxygen and nitrogen, and then the 2p orbitals here. And we can also draw in what will be our bonding and anti-bonding orbitals. And I will do them now just really quickly. Now, I know this looks really confusing at the time being, but once I label all the molecular orbitals, it will make much more sense. So at the bottom energy level, so the lowest, we have sigma bonding of the 2s orbital. And here, the next one up, we have sigma antibonding orbital of the 2s. This is denoted with a little asterisk in the right hand corner. Then when we get to the 2p orbitals, it is more challenging as we have introduced pi bonding. However, we can always tell this by this is always given as these little 2 here. These will be both pi bonding, and the other lower lines will be sigma bonding. So let's just label them now. The bottom one is pi bonding, and we know this comes from the 2px and 2py orbitals. And this one here is sigma bonding orbital, and this is 2pz. And at the top, similarly, we have pi antibonding of 2px and 2py, and at the very top again is sigma star, so antibonding orbital of 2pz. Now we're going to fill the electrons in for both the nitrogen and the oxygen. What we want to do is put as many electrons as we can in lower energy levels. So we're going to fill the 2s2 up, and then we have 3 electrons left, and each one of those can go in each one of the 2p shells. And that is because if we put them together, we get repulsion, which increases the energy. So this is all the electrons in their lowest energy levels. And now we're going to focus on the molecular orbitals. So the same principle applies. Put in as many electrons as you can in lower energy orbitals. So for bonding here, we're going to have 2 in the anti-bonding here, 2 in each one of these pi bondings, 2 in this sigma bond, and 1 in this pi antibonding, and altogether that is 11 electrons. Now I'm going to quickly just draw in the lines to show you where these electrons come from, so which electron orbitals they come from and how this all kind of plays out. Just as a quick little tip for you, when you're doing your own molecular orbital energy diagrams, the antibonding should always be higher, or in easier terms, a bigger gap from the 2p's, in instance if we use this, then the bonding orbital should be. So, for instance, however, I've not done it on this diagram. As long as you make a note of it, you should be okay. But this gap here should be larger than this gap here. However, this isn't always the case when we draw them. Sometimes we don't give enough space for them. So, just a note, just to write that antibondings for both pi and sigma should be larger gaps than sigma and pi bonding. From this molecular orbital diagram, we should be able to work out whether NO is paramagnetic or diamagnetic. So, as you should have learned from the key terms part of this course, that paramagnetic is when there is a single electron in a molecular orbital, and diamagnetic is when all the molecular orbitals that have electrons in are paired. So as we can see here, this one in the pi antibonding is unpaired, so we must have a paramagnetic. Now from this we can also calculate bond order, and bond order calculation is when you take away the bonding electrons away from the antibonding electrons and divide by 2. So for NO we have 8 bonding electrons and 3 antibonding, and that divided by 2 gives us a bond order of 2.5. And I'm just going to highlight where I found these electrons, just so you know where they are. Now, as we've worked out bond order, we can also work out which will be more stable. So we've got NO plus or NO minus. NO plus, we know that we're removing an electron, and the way we'd want to remove it is from the highest energy orbital. So this would be the pi antibonding, so removing it from the antibonding, which I'm going to denote as AB. And the opposite for NO, we're adding an electron, so again we want to add this at the lowest, which will again be the pi antibonding, so we put antibonding again. Now calculating the bond order calculations for both of these, so for NO it's 8 minus 2 over 2, and for NO minus it's 8 minus 4 over 2, And the answer for NO plus is 3 and NO minus is 2. 3 is bigger than 2, so NO plus is more stable than NO minus. If anything is still unclear after this video, rewatch it again, see if there's anything that you haven't picked up from, and when you are confident, complete the questions and get some feedback on our stories.